All right, we're doing section 3.4, which is concavity and the second derivative test. So we have a differentiable function on an open interval. The graph of a function is concave up if f prime is increasing and concave down if f prime is decreasing. So I drew a couple pictures to illustrate both of those. The first one is when f prime is increasing. Notice I drew a few tangent lines. The first one is negative, and then it slowly is getting steeper and steeper. So that means the derivative is increasing. This is called concave up. Concave up. Notice it kind of looks like a cup, so concave up is that's kind of easy to figure out. And then the next one is the f prime is decreasing, so notice that it starts positive and flattens out and starts becoming negative. This is called concave down. Okay. So our test for concavity, we're going to figure out how we can test this. We have a function and we have to find the second derivative. If the second derivative is positive, then we're concave up. If the second derivative is negative, then we're concave down. So it's very similar to increasing decreasing with the first derivative test. It's just the second derivative. So determine the open intervals on which the function is concave up or down. So the first thing we need to do is find the second derivative. Okay, f prime is -6 times x squared plus 3 is -2 times 2x, or -12x over x squared plus 3 to the second. Take the derivative again. X squared plus 3 squared times -12 minus f times g prime, which is the chain rule, all over g squared. I'm going to save some time. This simplifies to 36x squared minus 36 over x squared plus 3l cubed once we factored out at x squared plus 3 from every term. So we have to find out the critical points to this. This is equal to 0 at plus or minus 1. So it's the same thing as the first derivative test. We need to find where the second derivative this time, though, is either equal to 0 or doesn't exist. And it doesn't exist nowhere, so we just are looking for the zeros, and that exists at plus or minus 1. So we still have to make our intervals. This table is going to look really similar. From -infinity to -1, -1 to 1, and 1 to infinity. Still going to pick a test point. This time we're testing it in the second derivative and coming to the conclusion on the bottom. So I would test -2, 0, and 2. When it's -2, the second derivative is positive, just saving some time by plugging it in for you. 0 is negative, and positive for 2. So whenever the second derivative is positive, we are concave up, and concave down when the second derivative is negative. So our intervals, we are concave up from -infinity to -1, and from 1 to infinity. We are concave down from -1 to 1. Okay, just one extra step. Instead of first derivative, we're taking the second derivative. Determine the open intervals on which we're concave up or down. So we're doing the exact same thing again. Take the derivative twice. That's always the hardest part. Take it the first time, g f prime minus f g prime over g squared. Simplifies 2. X squared minus 4 already squared on the bottom. Okay, we're going to take the second derivative. G f prime minus f g prime, that's a chain rule. And again, after factoring out an x squared minus 2 from every term, this simplifies to 30 x squared plus 40 over x squared minus 4 quantity cubed. So now we need to find where that is equal to 0 or not continuous. And our critical points were not continuous at where x is plus or minus 2. So those are going to be the points that we need to test, because this function will never be equal to 0. Alright, let's make our chart. Our intervals are from negative infinity to negative 2, negative 2 to 2, and 2 to infinity. We need to pick a test point, test it in the second derivative, and come to our conclusion on the bottom. Our test points, so I'm going to pick negative 3, 0, and 3. We are positive, negative, positive, which is concave up, concave down, concave up. So our intervals, concave up from negative infinity to negative 2, and 2 to infinity. I do want you to rewrite your answer this way, and concave down from negative 2 to 2. Okay, a point of inflection. Let f be a function that is continuous on the open interval. C is a point. If the graph of f has a tangent line at that point, then that's a point of inflection, but it's only a point of inflection if the concavity changes from up or down to up at that point. If C f of C is a point of inflection, then it's either equal to 0 or doesn't exist. So those points that we were finding, those were our possible points of inflection. Determine the points of inflection and discuss the concavity of this graph. So we're going to actually do the exact same thing. This is really similar to the first derivative test. First we were looking for increasing, decreasing, and then we were looking for extrema. This time we're looking for concavity, and then we can find the points of inflection from where the concavity changes. So let's find the first derivative. This is an easy one. 4x to the third minus 12x squared. So the second derivative is 12x squared minus 24x. We need to find where that's either equal to 0 or doesn't exist, so I'm going to pull out a 12x. Our possible points of inflection, I'm just going to say POI, are those points we just found. X is 0 and 2. We need to test them. We can't say for sure that they are points of inflection until we're done making our chart. So we're going from negative infinity to 0, 0 to 2, and 2 to infinity. Picking a test point, we are testing it in the double derivative and coming to a conclusion. Our test points, negative 1, 1, and 3. Positive, negative, positive, when you plug those back into the second derivative. So we are concave up, concave down, and concave up. So we can note that because the concavity changes at 0 and 2, those are both points of inflection. Points of inflection at x equals 0 and x equals 2. We know that because the concavity changed. Okay, so that's just the second derivative test. That's exactly what we just did. We have a point of inflection if the concavity changes. So second derivative test again. If f prime of x of c is equal to 0 and the second derivative exists, then if f prime of c is greater than 0, we could have a relative min at that point. And if f prime of c is less than 0, we could have a relative max at that point. If f prime of c equals 0, then the test fails and we have to go back and do the first derivative test. So we can actually use the second derivative test to find the extrema. So we need to find the critical values. That was the first part. We needed to find our critical values, and that was from the first derivative. Okay, we can pull out 15x squared. We get 1 minus x squared. So our critical numbers are 0 and plus or minus 1. Then we need the second derivative. It's going to be negative 60 x to the third plus 30x. So we're testing only our critical points. We're not doing the inflection points this time. Okay, so our intervals. Oh, this time we're actually just testing the points. Excuse me. Point. Testing negative 1, and then we plugged that back in and got negative 2. Testing 1, 2, and testing 0, 0. Now we got these x values from our critical values, and we plugged them back in to get the y's. We want to know what the sign of our double derivative is. Because like it said up above, if it's positive, we have a minimum. If it's negative, we have a maximum. But if it's 0, we have to go back and use the first derivative test. So the sign of our double derivative, and the first one is positive, second one is negative, and the third one is 0. So this tells us we have a minimum at negative 1, negative 2, a max at 1, 2, but because we got a 0, this fails, so we have to go back and use the first derivative test. Since that was yesterday's lesson, I'm not going to go back and do that, but we need to go back and see what that point actually is. Okay, so that was everything new for section 3.4.